Good morning. Let us start today's class, which is on composites. So I think we will have this session on composites just for half an hour. I had given it for your assignment, but I think it's little bit bigger portion. So I just give you an introduction about composites. Actually, this is a book on nanomaterials and composites. So we will start with this chapter, 16th chapter. Okay, so the 16th chapter is about composites. So composites means it is just the mixture of two materials. There are no reactions happening between these two materials. So we are mixing two materials to get the properties of the best properties of those two materials to have it on the new material, so that we can use it for some application purposes. We should have the best properties of both these materials which are mixed. So that's why we can have more than two materials, but here normally we are considering only two materials. So we are mixing these two materials to get a composite. So we have here different types of composites. I will just show you some classification first. The composites examples are there. Many examples are there. You can see here in this chapter, the introduction chapter, it says about how a mixture is formed, a composite is formed. In different places you have applications. Mainly as you can see in the second paragraph, you can see that the applications are in aerospace, underwater, and bioengineering and transportation industries, like the extreme climate places. As we know that in aerospace, in space, you don't have atmosphere there, we don't have air there, so we have to have materials which should behave better in a place where there are no air there, so that those materials should be very strong. It should have special properties. So some metals may not be good in space, may not be working good in space. So we need to make composite materials. Like as you can see here in the picture in the beginning of this chapter, you can see the skiing person is skiing there. That skiing board is made of a composite material. You can see different layers of the cross section of that ski board is there. So different sections are made of different composite materials, which are very strong and which are not brittle. So these kind of applications are there in extreme sports, extreme bioengineering, like the the medical equipments which are going inside the body. It should be biocompatible. Those metals should not be affecting our body. It should not be harming our body. So those materials should be very well biocompatible. That should be made with these composite materials. So first of all, let us see how this material is made of. So we have many composite materials which are composed of two phases, and one is termed as the matrix and the other is termed as the phase. The matrix is the continuous part, the continuous and surrounds the other phase, often called, the other phase is often called the dispersed phase. So matrix phase, as you can see here in this picture, matrix is the continuous part which surrounds the dispersed phase. So the particles, the cylindrical shaped material is the dispersed phase, and the full body is made of matrix. So we can have different types of composites, as you can see here in this picture. it is the schematic representation of various geometrical and spatial characteristics of particles of the dispersed phase. Dispersed phase can be arranged inside the matrix in different way. As you can see, the A equation in the picture, the A part, the part A differs as with the concentration. The dispersed phase is less there in the top picture, and dispersed phase is more there in the lower picture of the part A of the given picture. See here, the concentration is higher in the lower picture. And when you go to the part B, picture B, you can see here the size of the dispersed phase is different. In the lower region, its size is bigger, and the concentration is also lower there. But here the main difference is the size of the dispersed phase. Upper picture is having lower size. And the shape, next one, C is representing the shape of the dispersed phase inside the matrix. So this is a composite material having differences about its concentration of the dispersed phase and its size and its shape, also orientation. Orientation is there in the picture E, and also D is the location, I mean distribution. Distribution is not in a same manner. The distribution of the dispersed phase is in the matrix, it is different in the lower picture and compared to the upper picture of the part D of the photo or the figure. So these kinds of differences are there in composites. Different composites you can make in this manner. So first of all, let us differentiate between different types of composites. So composites are of three types, mainly four types actually. First one is particle reinforced, second one is fiber reinforced, third one is structural composites, and last one is nano composites. So let us first look into particle reinforced composites. Here the dispersed phase is particles. So the particles are dispersed inside the matrix of the composite material. So that way it is made a composite material. So if you have large particles which are dispersed inside the matrix, then you can say large particle reinforced composites. And if they are more number and they are very small particles, then we can say dispersion strengthened composites. So particle reinforced composites are also divided in two ways, like large particle composites and dispersion strengthened particles. Now second one is fiber reinforced particle. Here the particles are in the shape of fiber, and this fiber can be oriented in different direction, and it can be aligned and continuous, and it can be discontinuous, and the fiber length can be short. So the fiber reinforced composites are divided into these two categories. First one is continuous aligned fiber reinforced composites, and the second one is discontinuous and short fiber reinforced composites. And again discontinuous fiber composites again divided into two, aligned and randomly oriented. So this way we have two types of we need to study only these two types, particle reinforced and fiber reinforced composites. But we should know the structural laminates and nano composites also. Structural composites, mainly laminates, that means multi-layer. Many layers of different materials are made in one time, in one substrate or something, and then that shows the property of all these layers. All these layers are different materials, so different materials shows different properties. So we should get all the good properties of all these materials together when you have the composite made in layers, made in multi layers. So we are calling that composites as laminates, structural laminates. So those are also used in many applications. You should remember that the composites are always used in aerospace, bioengineered materials, industry materials, and also in very complicated extreme conditions. You can use these kind of materials. Extreme applications, for extreme applications we are using these. We need to make it not man-made material. These are all man-made materials. These are not naturally occurring materials. Mainly they are man-made. So I have already said particle reinforced composites. They are divided into large particle and dispersion strengthened composites. Large particle composites contains large particles inside the matrix. Examples are concrete. One is concrete. Here many examples are written. You have to read it and remember those names. Okay. For dispersion strengthened nanocomposites, the particles should be lower in size. They are much smaller in size, 0.1 micrometer. They are in 0.1 micrometer to 0.01 micrometer range. Its diameter should be, the particle diameter should be in that range. Then only we can say it as dispersion strengthened composites. Okay, so large particles, nano composites, large particles, particle reinforced composites should use these two rules. Rule of mixture. First rule is we call it as the upper bound expression. You can see here in the red letter it is written upper bound expression. Large particle reinforced composites are. So you should remember this equation. The elastic modulus is equal to EM plus EP VP. EC is the elastic modulus. E and V denote the elastic modulus and volume fraction respectively. And the subscripts C, M and P represents composite matrix and particulate phases respectively. So EC means is the elastic modulus of the composites, the combined material, that is equal to EM. So EM is the elastic modulus of the matrix and VM is the volume fraction. How much volume fraction is there in that material, in that composite material by this matrix. So that is VM. So EM plus EP. EP is the elastic modulus of the particle and VP is the elastic volume fraction of the particle. This is the upper bound of the elastic modulus of composites. Then now lower bound expression is EC is equal to EM EP divided by VM EP plus VP EM. These two equations you should remember because we can plot the graph of EC of upper bound and lower bound like this for a material, tungsten material composites. You can see here EP upper bound and lower bound curves are drawn, and the real experimental value should be inside these two curves. So the dots are the experimental value of elastic modulus of the composites. So this is tungsten particle dispersed within copper matrix. So matrix is copper here, particles are tungsten. So this is the picture. So the experimental value of the elastic modulus of the composite should be inside these two curves. Now next example here shows this is the photo micrograph of a cemented carbide, cobalt cemented carbide. The light areas are cobalt matrix and dark regions are the particles of tungsten carbide. Tungsten carbide and cobalt, these are the material which is made to combine here. So these are the photo micrograph. Electromicrograph is also there. This is for reinforcing carbon black particles in a synthetic rubber. So rubber is also normal rubber which is used for making tire. they are not real rubber, they are mixed with some other materials. Carbon is mixed there. So that is also a composite example for particle reinforced composites. So this is a large particle reinforced composites. So this is picture of rubber. Carbon particles are there inside the rubber matrix. Okay, so concrete is also example, you can read that. Now let us move on to dispersion strengthened composites. I have already said the difference between dispersed strengthened composites and large particle reinforced composites. Here the particle size is very very small. The example here is the high temperature nickel alloys. Here the example is nickel alloys. In addition with the nickel alloys are combined with the 3% volume of thorium. Thorium oxide is called thorium. They are finely dispersed particles. Thoria particles are finely dispersed inside the nickel alloy material, and that is an example for dispersion strengthened composites. You should remember at least one example. The size also you should remember should be 0.1 micrometer to 0.01 micrometer. And now fiber reinforced composites, you can see here. Fiber reinforced, I have already said they are divided into two. I can see here in this picture they are divided into two, which is continuous fiber reinforced composites. Continuous means it should be aligned, and discontinuous, they should not be aligned, but they are short, the fibers are short, so we cannot make it aligned. As you can see here, I will show you one more picture here. There are fiber reinforcement picture is here. See here, this is a picture of fiber reinforced material composites. Schematic representation of the continuous and aligned one is A, picture A, continuous and aligned. The fibers are the red lines, and the matrix is the square there. And the fibers are longer in length, and they are aligned also. See, the second picture B is discontinuous but aligned. You can have discontinuous, continuous, it's not continuous, very short fibers are there inside the matrix, and they are aligned here. But see, you can see they are not oriented, aligned, randomly oriented. So they are short in length and but randomly aligned. Randomly aligned, not oriented in one direction. Okay, so let us see the influence of fiber orientation and concentration. So when you have continuous and aligned fiber composites, it might have a different property compared to the randomly aligned fiber reinforced composites. So these properties differences are written here. You should write it down and remember it. If you are asked for an essay, you should study these differences very well. So here in picture figure 16.6, it is written the deformation pattern in the matrix surrounding a fiber that is subject to an applied tensile load. So if you have a composite material using this fiber reinforced composite material, its property should be different compared to real just one material made of only one composition. So here the fiber is inside making a stress on the matrix. See here, the fiber is moving towards right side, and matrix is stretched along with the fiber, as you can see, because we are applying a load there. When you apply a load, you will see a difference in property in its composite material. So these things are the influence of fiber length. It depends on the fiber length, and also it depends on the concentration of number of fibers. So these all things you should make into consideration for finding its tensile strength, for finding its elastic modulus. They are all different when you have different fiber length, or when you have different fiber concentration, or when you have different shape of fiber. All these things will be different. This equation you can see critical fiber length dependence on fiber strength and diameter and fiber matrix bond strength. See here, critical fiber length dependence on fiber strength and diameter and fiber matrix bond strength. So this equation also you should remember, study well. Some critical fiber length is necessary for effective strengthening and stiffening of the composite material. So we are we are intending to have very strong material, so that they should not break when it reaches to space, or when it reaches underwater. Very high pressure is there in underwater. When you travel in a submarine or something, the pressure of water is very strong, so you should have a very strong material to make the underwater vehicle. Those materials should be composite material. So we should study its strength. The material strength should be studied by using this kind of making these kind of fiber reinforced materials. So the critical length LC is dependent on the fiber diameter D and its ultimate strength sigma F, and on the fiber matrix bond strength. All these lengths and details are depending on the strength of the composite material. So you can remember this equation also. Okay, only this much we need to study. If you wish to study little bit more, here you can see this picture also. You need to remember this picture: stress and strain study of fiber alone and matrix alone, and the composite. You can see the green line is the composite. See here, we will get a intermediate value of stress strain relationship there. The composite have stage 1 and stage 2 region. Two regions are there having different Young's modulus. Stress by strain is the modulus, elastic modulus. So these things you can remember. At least for an essay you should study. Prepare it. Write an essay about different types of composites: fiber reinforced composites, particle reinforced composites, nano composites. Actually, I have done my project, MSc project, in nano composites. Nano composites are extremely useful for making ferrofluids. We have already studied about ferrofluids and ferromagnetic materials, isn't it? All these things they are all interlinked. Material science combines many subjects. Actually, chemistry and physics, they combine many subjects. So all the chemistry students also knows these about these composite materials and ferrofluids and different things which we study. So actually, material science is a intermediate connection link between the physics and chemistry subjects. So you can read this at least this much, till this much page you should read, and then study well for your exam. Okay.